In this video, we're going to talk about momentum, and specifically what is momentum and what factors affect momentum and what happens to the momentum of objects when there's something like a collision. So we're going to start with this little picture here on the left, and you can see there's a train that collided with a car. And in terms of size, these are both relatively big objects compared to a person, but a train has much more mass compared to something like a person or a car. And obviously there was a collision here between these two things. And you can see the car was pretty much dominated by the train. You can see the car has some broken windows. There's some body damage. It got pushed up on top of the train. It kept moving. The train almost looks unfazed, like nothing even happened to this train. And I guess what we want to talk about is what is the reasons for that and how that happened. So the first thing we want to do is kind of give momentum a definition using words. And this is something I got from a video a while ago. They defined momentum as the quantity of motion of an object. So what that kind of says is if I look at this train must have more motion than what this does. And this car has less motion than what this train does. And it's kind of why the train probably just kept on rolling right through the intersection or the railroad crossing with this train or with this car on its front and didn't really have any effects of having to carry this extra weight. And we know trains carry massive amounts of cargo from point A to point B, so that's not surprising that a train car is able to push this car with any issue. It also does give us a little insight, though, as why things like gas tankers, semi trucks will always stop at railroad crossings and make sure there's no car, because if they got hit by a train, it would obviously be devastating to the cargo they're carrying, the person involved, and everything else. So to make that a little more understandable, we're going to define this using a formula now. Now the formula for momentum is kind of weird. It is P, and P stands for momentum, is equal to mv, where m is mass and v is velocity. So I guess if I go here, P equals mv. If we're looking at our train and car, well, the mass of a train is probably hundreds of tons. This car might be 1 or 2 tons. So even if this train is barely moving at all, maybe it's only moving 5 meters per second compared to a car which could move up to 25 to 30 meters per second if it's traveling, anywhere from 60 to 55 to 65 miles per hour. This train, though, is going to have much more momentum because of its massive amount of mass. Another way of thinking about this is what would hurt to get hit by more? And obviously, this train is probably the most devastating thing to get hit by. But not everything has to be big. You can take something small like a bullet, and you would not want to be hit by a bullet, because even though a bullet might have a very small mass, it might have 1,000 or more meters per second for velocity. So it can also be a very devastating thing to get hit by. Some other ideas is that momentum is a vector, which means it has direction from earlier. And we can add momentum using vector techniques. So we might have to use some right triangle trig in understanding that if you don't know the direction of the momentum, it's going to be tough to add it up when we're talking about adding multiple momentums. And it's measured in a unit that's derived called a kilogram times meter per second, or for IB, it's a kilogram times a meter times a second, oops, not a meter, but a second. Second to negative 1. And that's a derived unit. So those are kind of our real simple ways of defining what momentum is. And I think we all have an idea of what it is fundamentally. If you're walking down the hallway and a big person runs into you, you probably are going to get knocked backwards a little bit. Where maybe if you went over to one of the elementary schools and you're walking around the corner in one of those hallways and you bump into a little kid, they're probably going to get knocked backwards and possibly on the ground, and you end up looking like a big bully. So that's kind of our fundamental ideas of what momentum is. And for the most part, it's not too bad. We have a basic understanding of what these things are. So one major idea that we're going to bring up here is that momentum is always conserved. And that's kind of defined in the next two bullet sets after that, meaning there's always going to be the same momentum before and after some event. Now, the event could be a collision, it could be the firing of a gun. We'll talk about that in a second. But the momentum of those systems only change when outside force causes something to have a change in velocity. So momentum will always be the same. Assume that it's always going to be constant. And if you kind of just keep that as an easy way to remember things, that momentum never changes and not really even worry about the force, you should be just fine. For example, many of us have fired a gun. We live in Wisconsin. A lot of people hunt, and they know that a gun will kick back. That's like our velocity of the gun. And a bullet, I'm trying a little tiny bullet here, the velocity of the bullet will be forward. Now I'm drawing a bigger arrow here than what comes back. The velocity of the gun is backward, the velocity of the bullet is forward. Now before, I guess if I want to say the starting momentum is equal to 0. What does that mean? That means before we fire the gun, there's 0 momentum. So after we fire this gun, we know that because there's a velocity backwards, there's going to be some momentum going backwards. That might be a negative momentum. In this, let me just label this gun. And the velocity of this bullet is going to be going forward, and that would be a positive momentum. But because our starting momentum was 0, our final momentum, which is just going to be the momentum of the gun plus the momentum of the bullet, must also equal 0. So we're saying this momentum here is the exact same momentum except for the direction as a gun going backward. That's why you want to make sure your gun has a lot of mass, or at least the gun should be much more massive than what this bullet is. Because if this gun and this bullet had a similar mass, this would kick back with the same speed that this is going forward, and obviously that would be very damaging and dangerous for the person firing the gun. So that's why guns typically are much bigger than what the bullets are that you're firing. So that's our idea behind momentum is conserved. If we start with 0 momentum, we must end with 0 momentum. So in this case, even though things are moving afterwards, you have to also remember that the gun kicks back, and whatever backward momentum the gun has, the bullet is going to have that much forward momentum. So I'm going to run you through some example problems to see if we can continue to build on these ideas, and eventually we'll move to the idea of impulse, which is coming up in a little bit. But our first example, before the collision, now this is before these two cars hit, our velocity of the red car was 15 meters per second, and the blue, or not the blue car, the green car, I have that labeled wrong. I apologize for that, but that's green. Green car was at rest. So, before the collision, the green car is not moving, the red car is. After the collision, the two cars hit and stick together, and we want to know what is the new speed of these things going to be. If we ignore things like friction, we'll assume that the people didn't put the brakes on, and we don't have to worry about the deforming of the car that's getting beat up and the sound it makes. We're going to make this a very simple problem, relatively easier on you. So, the initial or starting condition, starting momentum, only came from the red car. P equals mv. We have a 1,000 kilogram car that's traveling 15 meters per second, which means the momentum of this, and we'll just say it's positive because they both end up moving the same direction, is 15,000 kilograms times meters per second. Going to the right. So that's the momentum we start with. That also must be our final momentum. Because whatever momentum we start with, we have to end with. So again, now that we know this, we just go to our new momentum. Now we have to think about what changed. So instead of having one car moving, this time we have two cars moving. So we have a new mass. That's equal to the mass of the red plus the mass of the green. Sorry about, again, the blue idea. So that's going to be simply 1,000 plus 1,200 kilograms, which is just going to be 2,200 kilograms. So now we want to know, well, what's our final speed going to be? So again, if I just do a P equals mv, put in our numbers, 15,000 kilograms times meters divided by second is equal to 2,200 kilograms times v. Now I'm running out of space, but my velocity here is going to equal 15,000 divided by 2,200. It's about 6.8 meters per second, and still going to the right. So in this case, our speed decreased, and it definitely should. It decreased by more than half because our mass increased by more than just doubling the 1,000. So you kind of see that both of those factors affect it equally. Our last example is what happens when you have something above the Earth, like a package, and obviously this is not drawn to scale by any means. This would be just a massively huge thing that only weighs 10 kilograms. But we just wanted to have a little reference of what the Earth is and what the package is. Again, we're starting off with zero momentum. The initial momentum, Pi, is equal to 0 because nothing's moving. The velocity of this is equal to 0, and the velocity of the Earth, for our purposes, is equal to 0. So we have no starting momentum. But we know when we drop things on the surface of the Earth that eventually these things do get some speed. So after a certain amount of time, the velocity of this is now going to be 10 meters per second. And the question up here is, if we release that and it strikes the Earth with 10 meters per second velocity, is the momentum conserved? And we're asked to support our opinion. So the idea here is we're going to have some type of momentum generated that's going in a downward direction. And that would be the P of the 10 kilograms. So the question is, where does the rest of this momentum come from that makes this go away? And the only way to get to this condition of having no momentum again, meaning we're going to have some momentum going upward, and the only thing that's there to generate that momentum is the Earth. Well, that probably seems kind of odd, that we have the Earth and it's moving upward somehow. But that's true. When we learn about gravitation later, we find out that the Earth pulls us down, but remembering back to Newton's third law, the Earth is then pulled up by us. So we have an equal and opposite reaction force to everything. So what we want to do is kind of try to prove this to you mathematically so you're not confused by this, because otherwise it seems kind of odd that every time something falls, the Earth should jump up, and we should notice the Earth is like constantly vibrating back and forth. But there's a huge difference in one of the things here. So when I calculate the momentum of this box, it's just simply going to be 10 kilograms times 10 meters per second, which is just going to give us 100 kilograms times meters, not divided by, let me change that, times meters per second. And that's going downward. And if we want to say downward is positive, then we'll just leave that as positive 100. So momentum of the Earth is equal to negative 100 kilograms times meters per second. So now we want to do is figure out what happened to this. And we notice this little helpful number here, that the mass of the Earth is 5.96 times 10 to the 24th. There's our huge difference. We have a 10 kilogram object compared to something that's much, much more massive than that. So we fill in our stuff. We have negative 100 kilograms times meters per second is equal to 5.96 times 10 to the 24th kilograms times v. So now I want to divide both sides by 5.96 times 10 to the 24th to get velocity by itself, and end up getting negative 1.7 times 10 to the 23rd, negative 23rd, sorry, meters per second is equal to v. Negative makes sense because it's moving the opposite direction of our box. And if I did this longhand, which I don't normally want to do, but I'm just going to do it today. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 20, 21, 22, and 17 for 23 meters per second. This is an unperceivable amount. And right, unperceivable, apparently that's a little tougher for me to do than I thought. But this velocity, this 22 zeros, 17 meters per second, is just so tiny, so small, that it really is not noticeable, that we would not feel the Earth shaking back. And it's because of that huge difference in the mass of the Earth compared to the mass of our mass that's being dropped here. So that's our video on momentum and its conservation.